Okay, so we're going to go over this new amino acid worksheet, and I'm going to give you some more particulars to think about. In this new amino acid worksheet, I am showing you the R groups that have charges. Okay, so um, and of course I'm going to talk about the disulfide bridge and polarity and nonpolar and all the little details that some people want to have. And again, let's get started. So let's first start with identifying those R groups on amino acids that are nonpolar. Now right away, if something is nonpolar, we're going to consider this to be hydrophobic. Hydro, water. Phobic means you're scared of water. Does that mean that nonpolar R groups are afraid of water? No, it just means that they prefer themselves over water. And why is that? Well, because nonpolar compounds have an equal distribution of electrons throughout their molecule. There's no real negative or positive area. So really, water has a tough time trying to really attract. It's got a negative end and a positive end. Water's a permanent dipole, but it has a tough time attracting something that doesn't have a negative or positive end. It does attract it a little bit, but it has a tough time. Water attracts itself very, very, very significantly in what we call H bonds. And what this means is this H that is attached to this oxygen. I know I'm drawing a bond by a dash, but this pair of electrons are really closely held to the oxygen. Oxygen has 6 valence electrons, and I'll draw it in. And of course, hydrogen has 1. But these pair right here are pulled in so very close, okay, to the oxygen end. This H doesn't really feel those electrons anymore, and that's the positive end. So what happens is we have an attractive force. The positive end of the H attracts the electron-rich area of the O, and this is what we call an H bond. Although they call it a bond, bad name, it's an attractive force. So the key here is that water strongly attracts itself. Right? Here's a water molecule, and here's another water molecule. They attract themselves by these intermolecular attractions. Remember, these are intermolecular. Intra is the bonds. So they stick together pretty darn strongly. This positive end attracts this negative end of the oxygen because, again, it pulls the electrons up, electron rich. And this is a pretty strong force. So if water is sticking together pretty significantly and strongly to each other, it's going to have a hard time leaving each other to have weak attractive forces. So we say hydrophobic, but understand, water prefers its own attractions with itself, or it prefers the H bond with other things that can H bond. So it isn't that water and water don't mix. They can mix. It's just that water prefers itself. Why would it break this strong attraction to have a weak attraction? It just actually has a hard time getting, overcoming its own attractive force. For water to leave water and to go to another particle to surround or dissolve, it's got to be almost either the same attraction or a greater attraction. And because fats have weaker attractive forces, water has a tough time leaving itself to get to the fat. And so therefore fats are left alone by water, okay? And water doesn't interact. So let's go find our nonpolar and let's color it the same color because I can. This is nonpolar. There we go. So alanine is nonpolar. And you may say, well, why, Mr. Grotsky? Because if I draw the carbon, okay, and carbon's bonding to this chain here, and I know this says CH3, but the H's, okay, are bonded outwards like this. Carbon and hydrogen have about the same attractive force. We use the word electronegativity. So if I put the pair of electrons, remember carbon has 1, 2, 3, and 4. And then hydrogen, we'll just change the color here, has 1, 2, 3, okay? So what's happening, and these pairs of electrons are basically shared right down the middle. And because of that, the electron density of this group is the same throughout, okay? And so there's no negative side or positive side. So that's easy to identify. Okay, this one has a charge. Therefore, it can't be nonpolar. It has one polar, so we can't do this. Okay, this one has this oxygen or a nitrogen here, and having an oxygen and nitrogen emits among, I should say, carbons and hydrogens means that these guys right here, because they attract electrons so great, there's going to be some electron-rich areas on this side of the molecule, and this side of the molecule is going to be different than this side. and therefore this looks like something that could not be a symmetrical distribution of charge here. So therefore, I can't make this uh, nonpolar. For the same reasoning here, I have O's at this end. There's CH's at this end. There's more electron density. We're pulling. Most electrons are over here. This isn't a nonpolar. Now, if I go to L-Cysteine, and this is something different, please pay attention. This sulfur, okay, is different than the carbon. So we would expect, based on what I've taught you, that L-Cysteine to be a polar molecule and therefore not be nonpolar. But just pay attention. Can this H here, H bond, here's sulfur, and let's just blow it up. Here's the H. That pair of electrons between the two, okay, are probably shaded toward the sulfur, but they're not pulled away so far that much. See, sulfur isn't one of our Phenylalanine elements, okay? These three are the most electronegative, meaning they pull an electron so great they leave the other areas deficient of electrons, which we call positive. So sulfur isn't one of those three, so it doesn't pull this pair enough. So this is not positive enough to attract another negative end of F, O, or N. So this does not H bond. And what did I say? Water loves to H bond with itself. So because sulfur doesn't create an H bonding opportunity, water doesn't really attract this guy. So therefore, this R group, even though it looks a little asymmetrical and has a difference, isn't very hydrophilic. In fact, because it doesn't H bond, water doesn't prefer to be around it. We're going to consider this to be nonpolar because of that. Okay, so let's move down and see what we got going on here. So let's go to glutamic acid, and you notice it has a charge. So because it has a charge here, it can't be nonpolar. It's got some pole here. And for reasons we explained, glutamine has O and N attract electrons really well. So this is going to have an electron-rich area, which is going to be a what? Not a symmetrical distribution of charge. All right, an asymmetrical distribution of charge. Here, I found something that I think I can use. This is just a hydrogen. Okay, it doesn't bond with anything. It's got one electron, one proton. Hydrogen is an atom. Atoms are neutral, and of course, there's no other, charge. One electron, one proton. That thing right there is essentially nonpolar. Now this has got a charge, and for reasons it's got a charge, it's got a an area of positive, so that can't be nonpolar. And here what we have here, hydrocarbons. Anytime we see a bunch of what? Hydrogens and carbons, for what we talked about over here, even though this shape may not look like symmetrical, what is even throughout is the electrons, because they share electrons evenly throughout. So anytime you see just hydrogens and carbons, you know that whole thing is nonpolar. So moving down, where else do I have some nonpolar R groups? Oh, right there. Okay, for leucine. Leucine, okay. And oh, we got a charge here. That's going to kind of wipe us away from being nonpolar, because you have what? Electron, what's a positive? It's got some charge. It can't be nonpolar. There's at least one here. Okay. Now, this guy, for reasons that is the same because of cysteine, right? Okay, this guy's got a sulfur, and so and it's got this. See, we said this guy right here was what? It was nonpolar. So for the same reasons, we're going to consider this to be nonpolar. And why? Well, in this case, it doesn't even have an H that could have a possibility to H bond. So even though there's some polarity, I would agree this sulfur does add, okay, a little bit of electron density here. There's no opportunities for water to H bond. And if water cannot H bond, it has no opportunity to H bond. It's not going to H bond with these H's, because these H's are not electron deficient, right? They have to be with an N, O, or F, and there's no H's coming off this. But even if there were, just like cysteine, okay, that you could not create an attractive force that water would like. So because water doesn't really interact with this because it can't H bond, we're going to consider it to be nonpolar. Now right here, what's going on here? Well, in phenylalanine, okay, remember that was the amino acid that was what? Missing, okay, or I should say it's the amino acid that causes PKU. We talked about that disorder. We don't have the enzyme to break that down. But right here, talking about what's in phenylalanine is this non-polar, okay, group. Now, this is a hexagon, but in the corners of the hexagon, as I've told you, here are the carbons. And if you look carefully, at every corner, there's a carbon. And they do this in organic chemistry. They like to show the carbon backbones. We can see examples here. Now, if you look very carefully, this carbon has 1, 2, 3, 4 bonds. So this carbon doesn't need any H's. This one has 1, 2, 3. So we need an H here. Okay, H's are emanating outward here for these guys. You don't have to know this, but essentially, if you just see a structure like this with no elements, it's carbons and hydrogens. So therefore, by the way, they call this a benzene ring. This is totally nonpolar because of the hydrogen and carbons that do what? Share electrons equally. Okay, it is very symmetrical too, and there's a symmetrical distribution of charge. This could be nonpolar if this was a carbon here, right? The rest of this, as we've talked about, are carbons. Now this is a carbon here, carbon here, carbon here. There'd be an H coming off this guy because carbon must make 4 bonds, and we use the H as the fillers. Now this carbon makes 1, 2. So we need 2 H's, and you get the idea. But because of this N, who is part of the Phen, who really attracts electrons really well, you're going to have a rich electron density here, and there will not be a symmetrical distribution of charge. Most of the charge, electrons will be pulled toward the N, and that makes it definitely not nonpolar. Okay, same reasoning for the O in this R group for serine. Okay, this O is going to pull electrons toward the N, and it's going to make an electron-rich area. Same thing for this O here. So these guys are amino acids that can't be nonpolar. And for the same reason, this N is going to create electron-rich area. So therefore, there's going to be an asymmetrical distribution of charge pointing toward the N. And for the same reason, this O creates an asymmetrical distribution of charge as they get pulled toward the O. But I finally find an R group where there's going to be a symmetrical distribution of charge. Hey, carbons and hydrogens always do that. All right, and we push forward and we see that I got to the end, and so I found all my hydrophobic, okay, R groups. So let's go find our ionic R groups. And why do I care about the ionics? Because they're going to stick together, okay, by something called ionic attractions. A positive is going to attract a negative. Now let's not forget, before I go on, the nonpolar are going to stick together, okay, by something called LDF forces. And these are basically weak attractive forces. Sometimes you can say weak nonpolar forces. So nonpolar, I should say, nonpolar R groups, okay, as we have identified with this color here, with this highlighting, will stick together because of electron clouds that I've taught you that shift ever so slightly when they come in contact. Two come together, these electrons repel these guys, and these guys will move toward it and make very small negatives and positives. When they move away, they turn off. In any case, you can just say that they're nonpolar attractions, or LDF forces. So nonpolars will attract nonpolars, and that's called hydrophobic. Okay? And we have a thing in chemistry called like attracts or dissolves like. So nonpolar will attract nonpolar. And again, they prefer each other mainly because water, again, can't attract, has no ability to overcome its own attractions to get to something weaker. But ionic attractions, okay, let's go back to that kind of coloring there. Ionic attractions are due to a positive R group, permanently positive, and that's what I've added in this new formula, this positive attracting a negative. So these two would interact, okay, in a tertiary structure. So all I'm looking for is charges, and I left those out today. Sorry to do that to you. I'm just trying to make up for it in the best way that I can. So I made a lecture, okay, and so I'm just going to find all my positives and negative, permanently negatives. I think I got them all. So those are of the 20 amino acids, okay, I think the ones that have a charge that I can see are the ones that I found. All right, and there we go. Now, these guys would have ionic attractions between the R groups in a primary chain when the protein folds. And let's go on to polar. Okay, well, the one remaining is the polar, and for reasons we explained, polar, okay, are going to be the R groups that have a asymmetrical distribution of charge because of an O or an N, okay, that pull on the electrons and create an area in these R groups that's going to be the negative end. Okay, so every one of these R groups, if you look at it carefully, okay, have an N, oops, I don't want to do that, okay, have an N or an O somewhere that's doing what? Creating a negative area in that R group. Now, of course, nonpolar doesn't have it. Okay, we don't consider a charged R group to be polar because the whole thing's +1 for reasons I'm not going to explain in this video. So every one of these polar molecules is polar because of an O or an N. An F would work too, but you don't find them in organic molecules. All right, that creates more electrons in these areas than others. All right, and we would say, okay, that the polar and the ionic, okay, now I'll say this, they're considered to be hydrophilic. Now the reason why I'm including the ionic is because they have a charge. Now you say, well, Mr. Grodsky, are they H bonding? Well, they could possibly, but this positive will interact with the negative part of the water, which is the oxygen end who pulls in the electrons. Or the negative end, okay, of this charge what could attract the positive. Is this H bonding? Well, it could possibly be considered somewhat in between. But what I'm going to say to you is because of the positive negative charge and because water has a negative side and a positive side, two poles, it's called a dipole, there is some interaction. And so we could say that ionic is hydrophilic. Now, the best hydrophilic is polar, and it's the reasons why, because every one of the polar ones that I drew, party people, can H bond. This H can H bond. It's hooked up with an N. And I'll say it for the last time, sorry for repeating myself. This H, these electrons are pulled so far away. This is the electron rich area, negative. This side has nothing but a proton left, and it's positive, and that's the positive that contract another ON. Okay, and so you can find yourself in every one of these polar or green R groups an H that can H bond. Okay, and so every one of these polar molecules, okay, represents an opportunity for H bonding to occur, meaning water is going to love it. Why? It prefers itself. It's going to stick together really strong. The only way that water comes off of it sticks to something as strong. These positive or negative charges could be as strong. So that's why we're going to have to consider ionic as hydrophilic with the polar. But the polar is special. It's the best hydrophilic because the opportunity for water to H bond with this R group allows it to separate from the water. Okay? And that's really important. So the hydrophilic groups, R groups, and a folded protein will be more on the outside of the protein, not hidden like the nonpolar, because they can interact with the water. Whereas the nonpolar doesn't interact very well, hydrophobic, they're going to be basically pointed deep into the inside of the protein when it folds. Okay, so we've covered that. Now, the only thing we haven't covered, okay, is that there are some of these that make disulfide bonds or disulfide bridges. So cysteine is an example. Notice I have this carbon CH2, and let's just make some room here to explain this. Okay, now if I have another cysteine, and I'll just draw it, and so I have an amino acid backbone, I'll just draw it like that, and then our R group comes off as a CH2, and then we have a what? An S bonded to an H. These H's can be lost, well, will be lost with 2 electrons, and you'll make a bond right here. And that's the disulfide bridge or bond between 2 cysteine. We consider both to be nonpolar because water has no opportunity to really H bond with them, so water doesn't really attract them or move away from itself. And it's important you get that. So this guy right here undergoes disulfide bonds, and these are really strong covalent bonds. If you notice, sulfur has 6 valence electrons, so it's going to make a bond on one side and a bond on the other. Okay, so it's like a sulfur bonding to another sulfur, and this sulfur bonds somewhere else. Notice it makes 2 bonds. It has how many valence electrons? 1, 2, 3, 4, 5, and 6. Another, okay, sulfur has 1, 2, 3, 4, 5, 6. So they want to have 8, so it's something it bonds to here. So the idea is that sulfur is going to have 2 bonds, just like oxygen. And this is a strong bond. Therefore, this provides stability. Make sure the protein doesn't unfold. Also, the curl in your hair. Okay, now if you notice, there's another compound, methionine, that has sulfur. And you may say, well, why doesn't this undergo disulfide bridging? And the reason is this CH3 at the end is really a C bonded to an H, to an H, and to an H here. And this guy really is an H on one side and an H on the other. It's hard for another sulfur to come in contact with this because you have all this alkyl group, or these CH3 provide protection, so it's hard for molecules to get in here. So this doesn't disulfide bridge. And I know it's a little bit polar because there's a little more electrons in this area, but because water doesn't what? H bond with any of these H's, or sulfur, in this case it doesn't have an H, water doesn't really attract it, so therefore it's hydrophobic. Okay, so I hope that gave you a more detailed explanation of how these differ. Okay, and hope that helped.